All right, today we are diving into something that, well, it kind of powers our entire modern world, but in ways you might not even see. Welcome to Taming the Unknown, an introduction to estimation theory. Okay, let's just jump right in with a pretty wild question. What if I told you that the single most important number in your life is actually just a guess? I'm talking about numbers you rely on every single day for your safety, your money, for just getting from A to B. They aren't certainties. They're just really, really good guesses.
I mean, think about that little blue dot on your map app. Your phone doesn't actually know with 100% certainty where it is. No, it's constantly getting hit with all these noisy, messy signals from satellites, and it's doing its best to estimate its most likely spot.
Or how about the stock market? Those super fast trading algorithms, they're not just reacting to what the price is right now. They're in a constant state of predicting, of estimating where the price is going to go next, all based on a fire hose of complex, noisy data.
And then you've got the really high-stakes stuff. Tracking something like a missile. It's not about knowing its exact path down to the millimeter. It's about estimating that path with just enough precision to make a decision that absolutely cannot be wrong.
But here's the thing. This is not just random guesswork. This is the science of estimation theory. And honestly, it's like a mathematical superpower. It's how we manage uncertainty, how we correct our understanding of the past, and how we predict the future. And today, I'm going to show you how this superpower was used to find an entire planet that no one had ever even seen. So our story kicks off with this huge mystery out in the cosmos. A real crisis, one that threatened to tear apart everything we thought we knew about physics, and it all started with a wobbling planet.
So, back in 1781, Uranus is discovered. Awesome. Astronomers get right to work, right? They pull out Newton's laws of gravity, which were like the gospel of physics, and they map out its orbit. The math was beautiful, perfect. It should have been a nice, predictable path around the sun. But by the 1840s, it was clear something was seriously wrong. For decades, Uranus just wasn't where the math said it should be.
And you can really see the problem here. On one hand, you've got the predicted orbit, this perfect, clean ellipse. This is what all the physics, all of Newton's work said had to happen. But then you have what they were actually seeing through their telescopes, a path that was kind of wobbly, a little off, and that tiny, tiny error was a massive problem. I mean, could Newton have been wrong?
But then a couple of brilliant mathematicians came along and had this absolutely radical idea. What if the error wasn't an error at all? What if it wasn't a mistake in the math? What if the error itself was the clue, like a map pointing to something they couldn't see? And that's the moment everything changed. They stopped seeing that wobble as a failure of their model.
Instead, they started to see it for what it was: evidence. It was like a gravitational fingerprint left to the scene by some unseen culprit, a mystery guest pulling Uranus ever so slightly off its course.
And this right here, this is the absolute heart of estimation theory. The error is the information. By just looking at the pattern of that wobble, that little bit of leftover error between what they predicted and what they saw, these mathematicians could actually estimate the mass and the location of whatever was hiding out there. They used this cool technique called least squares estimation, which is basically a fancy way of finding the best possible line through a whole mess of data points. And in this case, it told them exactly where this mystery planet had to be to cause the exact wobble they were seeing.
And the power of this idea is just wow. So one of the mathematicians, Urbain Le Verrier, finishes his calculations. He sends a letter to an observatory in Berlin and says, hey, point your telescope right here. And what happened? They found Neptune that very night, less than a single degree away from where his math said it would be. Think about that. He discovered a planet with nothing more than pen and paper. So this incredible moment wasn't just some dusty old footnote in history. No way. It was the dawn of a whole new era. This ability to pull a clean signal out of all the noise, to turn a mistake into a discovery, that's the fundamental power of estimation. And it's a power we use constantly, every single day. I mean, the exact same logic that found Neptune is what we use today. That least squares method, it's how we track spacecraft with unbelievable precision. The bigger ideas behind estimation theory, they were used to process the data for the lunar module, helping it land on the moon with pinpoint accuracy. And then there's the famous Kalman filter. You can think of it like an estimation engine that's always running, always updating. And it's used to make sense of noisy data in everything from self-driving cars to the stock market. So if you wanted to boil it all down to one sentence, this is it.
Estimation theory is the math of intelligently predicting the future and correcting the past, all using messy, imperfect data.
Okay, so this isn't just about finding planets or landing on the moon, right? This skill, the ability to wrangle uncertainty and make sense of it is, and I'm not exaggerating here, one of the single most important skills you can have in the modern world.
It doesn't matter if you're in engineering, data science, finance, robotics, aerospace, you name it. The systems we're all working with are just flooded with noisy, incomplete information. And being the person who can step in, build a model that tames that chaos, and pulls out a clear signal, that is a legitimate superpower.
And if you want to develop the superpower for yourself, well, we've got a roadmap for you right here. First, we're going to master the fundamentals. Then, we'll dive into the awesome tools of the trade, things like least squares and the Kalman filter. And then, the best part, you're going to put it all together and actually code your very own intelligent predictor.
Look, the history is absolutely fascinating, but the real magic happens when you start applying these ideas. So next time we're done talking about old planets, we are going to start coding. We're going to build the simplest and yet one of the most powerful estimators in history. You are not going to want to miss it. So, you ready for lesson 2?
Awesome! Thanks for joining me on this first step into taming the unknown. I'll see you in the next one.